Hello and welcome to our first discussion in Chapter 3, Periodic Properties of the Elements. With this chapter, what's very important is that as we start discussing things transitioning from Chapter 2 into Chapter 3, quantum mechanics is still very much at the forefront of our discussion. We're just now going to see how quantum mechanics fits into the periodic table. So it'd be great if you had that periodic table handy. There's one in your textbook. You can find one at ptable.com, or you can just Google periodic table, and you can find one to keep it handy while you watch this video and while you do all the practice problems in class as well. Things that we want to start off with in this section is just looking at elemental patterns and why we have the periodic table. So reoccurring patterns that we see for both physical and chemical properties really aid us as chemists at predicting new elemental behavior and studying new types of reactions for elements. So for instance, aluminum versus indium. Aluminum's density is low. It's 2.7 grams per centimeter cubed. And when compared to indium's density, 7.31 grams per centimeter cubed, we can start to see that as elements, as we move down a column on the periodic table, aluminum is in row 13 on the periodic table, or column 13, excuse me, and indium is just two specific rows down. And what we see is that the density of elements tend to increase as you move down a column. And that's primarily due to the mass to volume ratio of the atoms increasing. And density, along with other patterns such as atomic radii and affinity of electrons, probability of losing an electron, all of those things tend to be familiar. And so when we start looking at the periodic table, we'll start looking at how can we look at an element's position on the periodic table and say something about it? Is there somebody next door that is similar in reactivity? And that's where we'll be able to really use the periodic table as a tool. You will always have a periodic table with you when you take an exam. That is not something that I need you to memorize, but what we want to be able to do is look at that periodic table and truly use it as a tool. Let's just get into a couple of elemental patterns. First, density was one. Atomic radius is another one. When we look at moving down a column, so this is just a pulled out version of that same column where we had aluminum and indium in the previous example. And what we see is density does increase. Boron's density is the smallest. Indium's density is the biggest. And what we see also is the radius increases with 85 picometers for boron all the way up to 166 picometers for indium. We'll talk about more about these trends and what really causes these trends. It's going to relate back to Chapter 2 and our quantum mechanics. But what we want to do first is really get a good review on who developed the periodic table. In 2019, we celebrated the 150th anniversary of the periodic table. Dmitry Mendeleev in 1869, he was a Russian chemistry professor, and he arranged the elements that were known based off of mass. It's actually a really funny story. Dmitry Mendeleev, very secluded chemist, he loved to play solitaire. And I imagine him just kind of sitting in his house with maybe a lab coat on because he's cool like that, playing solitaire and putting one element on each card. And what he noticed was as he would line up these elements, notice how you see here, when he would line up these elements by mass, he actually noticed that there were some reoccurring properties. Things like helium and neon and argon were what they call inert gases, things that do not like to react with other elements. Same idea with lithium, sodium, and potassium. These were elements that were metals, and they had a very violent reaction with water. So they all had to be kept under oil. When they were stored, they could react with the moisture of the air, and when they did react with moisture, they were explosive. Again, he went a little bit further and said, well, beryllium and magnesium and calcium all kind of react the same. They're not as violent as lithium and sodium and potassium, but they still do react slightly with moisture in the air, and specifically with water. And so looking at um, how Mendeleev set up the periodic table, he was doing it first off of the idea of increasing mass. And then what he noticed was that certain elements had very similar properties. And so he started to line up those elements. Think about solitaire, how we ever played solitaire. If you learned it as a kid, it might be a lost art now, but my family was big on card games. So solitaire is one where we put the cards on top of each other, and we make columns with the cards based off of certain properties, red versus black, an order of numeric value. So what Mendeleev was really doing was starting to look at a couple of different properties, physical and chemical, so mass and reactivity, and align these elements in a specific way that made sense to him. What's amazing about this is that quantum mechanics, which was discovered or developed, 70 years later, actually explains the electronic structure of the atom and its properties. And therefore, when we look at the periodic table, we can see the beauty of how it was set up, not only by simplistic things like mass and reactivity, but also see how quantum mechanics plays a huge role in its organization. So Mendeleev's periodic table, he was trying to make sense of certain patterns. He was a brilliant chemist, and for one main reason that I admire him so much, at certain points, he actually left spaces in the periodic table for elements that he knew didn't exist at the time, but he predicted could have existed. So he would call them EKA aluminum, comes after aluminum. Gallium was not discovered yet in 1869, but because when he was setting it up by mass and properties, he knew that something could be after aluminum that had specific properties like the other things around it. Specifically, if you look at gallium on the periodic table, it's right underneath aluminum. And so that's where he said, you know what? I see what aluminum's properties are. Maybe gallium is similar. And so when he looked, and these are what he predicted. He predicted that the atomic mass was around 68 AMU. He predicted that its melting point was low and its density was around 5.9 grams per centimeter cubed. He figured that it would form an oxide just like aluminum does, Al2O3. And he figured that it would form the same type of chloride compound as aluminum does. And so what he was really trying to predict was elements in the same column have similar properties. Look at the actual properties. This was incredible for the time. That density is really ridiculous to me to think about. It's spot on, and he was only predicting based off of what he saw in this beautiful pattern of repetition of physical and chemical properties. He did the same thing for germanium, which is right next door. It's underneath silicon. Silicon was an element that was discovered, so he named germanium, EKA silicon. And so when he looked at those types of spaces in his periodic table, he was trying to think of beyond what was there and think of what's coming next. And he was pretty close in a lot of things. If you look at the first periodic table, you can always Google. We're still up on the high of the 150-year anniversary of the periodic table. So I'm sure you can find some other things that were out there in existence. There were other periodic tables that were being developed at the same time, but Mendeleev's was the most organized, that matched and left spaces for things that were undiscovered at the moment. There are some interesting ones out there. I'm used to the periodic table, so I'm a little biased to other ones, but you know, whatever one works. Mendeleev's works the best. The modern periodic table, what's its format? The elements, again, are still listed in order of increasing atomic number. Why we don't do increasing relative mass anymore, as they were on Mendeleev's table, is that we know about isotopes now. And so there are some very rare cases where an element with a larger proton count actually has a lower mass. And that's only due to the fact that isotopes exist, and some isotopes are more abundant than others. So we do it by something that's a little bit more concrete now, which is atomic number. It is increasing in atomic number, so we do have that structure on our periodic table. The rows going across a row is often called a period. Going down a group is often called a family. Sometimes they're called groups, going down that column. But like I said, they have that familiar type of physical and chemical properties. So things like helium, neon, argon, they're part of the same group or family. They are called the noble gases. We do have fluorine, chlorine, bromine is underneath that, and iodine, those are called the halogens. The only one that is kind of left out is hydrogen. Hydrogen is over there in column number 1. Column number 1 are called the alkali earth metals. We'll get to those specific names a little bit later. Hydrogen is not really part of group 1. It's over there because it's the first element, but in reality, where it should fit is very similar to fluorine, chlorine, bromine, and iodine. It's not the same, it's kind of in between. So hydrogen is in its group all by itself. It doesn't even have a family. Kind of sad, but he's actually multiple families. When Mendeleev, again, developed the periodic law and the periodic table, he put the elements in patterns, but he did not explain why the patterns were what they were. He was really amazing at predicting which spots needed a filler element, or how many families they had that there were at that specific time. However, he knew nothing about how the actual elements reacted. And so the periodic table is specifically a law. It predicts the patterns, but it does not explain why. It is not the theory behind anything. Quantum mechanics is still our theoretical basis for how and why things react. Okay, groupings. Again, we'll see a couple of different ways to talk about the periodic table. What I would suggest at this point is pulling out a periodic table again, and kind of honing in on these specific groups as we dive into it. I know the online format's not the best, however, we'll do a lot of this practice in class. What I want to be able to do is just look at a periodic table and name a couple of things. Specifically, when we look at our periodic table, here's mine, I'm in the chemistry lab. When we look at this periodic table, a couple of different things we can see: metals, nonmetals, and metalloids. Now, what I would suggest if you had a colored copy of the periodic table, like the one that's in your textbook, it would be the best type of analysis. Maybe you can see it, maybe not. Best type of analysis to understand who is a metal and who is a metalloid and who is a nonmetal. All of the yellow in your textbook, if you have the e-text, you still have this, or you can find it on ptable.com. All of the yellow are metals. Even down here, this column or this row of the lanthanide and actinide series. We see over here in the purple, those are the metalloids. They're not very many metalloids. And over on the far side, the far right-hand side of your periodic table, that greenish color in your textbook, those are the nonmetals. So when we think about the breakdown of the periodic table, we see about 75% are metals and about 25% are nonmetals. So yes, a few metalloids in there as well. Those classifications, we're going to be able to dive into seeing why they are what they are as we get further in our discussion in Unit 2. The periodic table can also be divided into main group elements, and those are elements whose properties are very, very predictable. The main group elements, if we just count across, it's hydrogen's group 1, beryllium's group 2, all the way across to boron in group 13. Sometimes on the periodic table you might see 13 written on top of boron, or 3A. Depends on which way your periodic table is labeled. If your columns go 1 through 18, you'll see a 13 up there. If your columns go with A's and B's, you'll see the A's are the main group elements. But boron, carbon, nitrogen, oxygen, fluorine, and helium, all of those columns or families are the main group elements. The middle section from scandium to zinc, atomic number 21 to 30, those and their families are what we call the transition elements, and the inner transition elements or transition metals are the lanthanide and actinide series. Now the transition elements, the lanthanides and actinides, they have somewhat predictable properties, but not a whole heck of a lot. When we look at them, yes, we can kind of see some trends, but there's really variations with them. And that's pretty much because of where their outermost electrons are. So we're going to get into looking at this periodic table and being able to really start to label things. Again, here's some things that we talked about: main group elements. Your textbook has both the A's and the B's, and also 1 through 18. Old school is the A's and the B usage. There's the B's for the transition metals. You can also see a new method where we just go straight across and count 1, 2, 3, 4, 5, 6, 7, 8, all the way up to 18. Doesn't change anything, it's just a way of counting, right? So the main groups are the A's, or 1, 2, 13 through 18, and the transition elements are the B's, or 3 through 12. Either way you slice it. Again, the inner transition elements, right there, the lanthanides and actinides, they are just as unpredictable as the transition elements are. You can call them transition elements, or you can call them transition metals. They are metals. Now, when we look at the metalloids, some periodic tables like this one here, which was from the e-text version of your textbook, doesn't have the metalloids on there. So I'm just going to highlight them as purple. We have boron, silicon, germanium, arsenic, antimony, tellurium, astatine. That guy, the new one, 117, brand new. I don't really know what his name is yet. So what we see is this step down ladder that really separates our metals and our nonmetals. And that ladder you can kind of memorize as looking at where that transition is from metal to nonmetal. We're going to talk more about what does that mean and their reactivity when we get into periodic trends. Again, you do not need to memorize those things, but you do need to be able to look at a periodic table and identify where the metals, where the nonmetals, where the metalloids, where a transition versus main group elements. So again, things on the left are metals. This little corner over here on the right are the nonmetals. Lovely. All right. Now, we just came from the quantum mechanics chapter, and it was able to describe quantum numbers. When we took our quantum numbers, we were able to really locate the probability of finding an electron in the electron cloud. And so quantum mechanics is describing the behavior of electrons in atoms. We know where they can be found based off of the probabilities of quantum numbers. Now we're going to take those quantum numbers and change it into what we call the electron configuration, how an atom's electrons actually occupy the orbitals. We've discussed all the different orbitals and all the different options with quantum numbers, but now let's put it together and put it with the elements themselves. So when we left chapter 2, what we ended up saying is n can be any whole number 1 through infinity, but L is determined based off of n. N is the size of the orbital, it's the distance away from the nucleus. It also tells us the energy of the orbital. L tells us the shape. When L equals 0, that's the s orbital. From there, we can think about the ML and say that that is the range from minus L to plus L, including 0. And we do know that there is a spin of either plus 1/2 or minus 1/2. Now, what we can do with that is do a shorthand. We'll take the N value, we'll take the shape of the S value, and we'll be able to merge those together into an actual orbital location. Now, that orbital, 1 being N, and S telling us L, that tells us a lot of information about the energy, the size, and the shape. The number up here at the top in the subscript is telling us information about the electrons that we can put in there. And that's the new part in chapter 3 that we're going to be able to discuss. Now, hydrogen has only 1 electron in its elemental form. And so with that 1 electron, we want the simplest orbital that we can find. And that's what we'll see. When an electron occupies an orbital for an atom, it's going to try to be the lowest energy possible, the simplest energy possible. We know that the lowest energy would be n equals 1. And when n equals 1, that gives us an s orbital. And hydrogen can put its 1 electron in there. So we have an electron configuration for hydrogen of 1s1. That's how we would read that. You can also say 1s superscript 1, but I just like to say 1s1. That's the identity. Let's talk a little bit about the Pauli exclusion principle. This is where we actually get into the idea about m sub s, the spin being plus or minus 1/2. What does that even mean? Well, when we think about an orbital with a specific orientation, there can be 2 electrons in that orbital. That's what quantum mechanics is developing. The idea that we could have hydrogen, I'm going to rewrite hydrogen with its 1s1 electron and its orbital diagram, which is usually just a box that has the orbital name, the N and the L. It has 1 electron in there. But when we look at helium, why is helium so stable? It has 2 electrons, 1 meaning that n equals 1, s meaning that L equals 0, and that 2 up there tells us there are 2 electrons in that orientation. Now, we do know that ML equals 0, and how we get the 2 electrons in that orientation is by having one have an ms of plus 1/2, and the other will have an ms of minus 1/2. The Pauli exclusion principle says this: no 2 electrons in an atom can have the same set of 4 quantum numbers. Their N, their L, and their ML can all be identical, but what has to be different is the spin. And so when we think about that, we can have a maximum of 2 electrons per orientation. As we go and increase N, we know that L can have more options, and so then ML has more options. The only options we ever have for the MS is a +1/2 and a -1/2. They must balance each other, those electrons. And so no more than 2 electrons can exist in a given orbital. Okay, a couple of things. That idea of the Pauli exclusion principle was not developed until 1925, still in the time of quantum mechanics. It was discovered or developed by Wolfgang Pauli, who really was trying to emphasize the idea of energy levels of electrons. A couple of other things that came out of this. The Pauli exclusion principle, I want to just rewrite so that we can know it's one of our home plates, right? It's one of our ideas that we have to carry throughout our discussion on electron configurations. Another one is called Hund's rule. Now, Hund's rule is the idea that degenerate orbitals have the same energy. We'll call that equal energy. So what are degenerate orbitals? They're orbitals of the same shape and size, just different orientation. So when we look at something like n equals 2 and L equals 1, this was the 2p orbital. ML, though, is -1, 0, and +1. There were 3 orientations, and if we remember, they were the X, the Y, and the Z. Now, in electron configuration, we again as chemists like to abbreviate things as much as possible. So when we think about the PX, the PY, and the PZ, they will all be encompassed in that 2p, and they're understood to all be there. There are 3 orientations, and each orientation can have 2 electrons. Why can it have 2 electrons? Because of the MS of +1/2 and -1/2. Each one can have a +1/2 and a -1/2. So 3 orientations, 2 electrons in each. To fill the 2p orbital, we can have 6 electrons. Now we'll learn a little bit more about Hund's rule. I want to just present it right now, but we won't fill up our diagrams for a couple more minutes. When we look at Hund's rule, the last portion of it says that because degenerate orbitals are equal in energy, right? Because the px, the py, and the pz are equal in energy. When putting electrons in these orbitals, when we start to see that how they react in the electron cloud, one electron gets put in each orbital first. Before pairing. What we're trying to build here is a couple of rules that help us overall understand how the electron cloud is formed as we put 1 electron, 2 electrons, 3 electrons, etc., all the way up. How do we build up the electron cloud from 0 all the way up to, let's say, 8 electrons? Pauli exclusion principle is the good first one. No 2 electrons can have the same 4 quantum numbers. Hund's rule is the second really good rule to follow. When we have degenerate orbitals, the px, the py, the pz, the same thing goes for the 5 orientations of the d orbital and the 7 orientations with the f orbitals. We put 1 electron in each before we pair. Now, why do we do that? Well, when we think about Coulomb's law here, this is Coulomb's law. This is a calculation that was known in physics, and it's a law that describes attractions and repulsions between charged particles. It branches off from the discovery of the electron in J.J. Thomson's cathode ray experiment. When we think about opposite charges, they attract. Opposite charges here, if we think of a +1 and a -1, Q is just a charge, +1, -1. What we see is that that +1 and the -1 multiplied together is a negative energy. Energy releases, which is a good thing. Energy is lowering. If we were, say, to have a +1 and another +1, that is energy raising or increasing. The 2 charges multiplied together creates a positive energy, which means not favorable, unfavorable. We're increasing the energy of the system. A -1 multiplied by a -1 for Q1 times Q2, that is also energy increasing. A -1 times another -1 is an overall positive value, which means, again, unfavorable. We're increasing the energy of the actual system or the atom. So electrons repel each other. That's what Coulomb's law tells us. And if electrons repel each other, we don't want them to be paired if we can give them the space that they deserve, meaning 1 in each. Let's just draw that out, 1 in each, so that each electron could have its own space before it pairs. If we have to pair, we will, but we'll try to give every electron its own space first. Now, along with these orbitals, we do have one more idea, and it comes from our last principle, which is called the Aufbau principle. The Aufbau principle literally is German for build up. It means that in order to build up my electron cloud, electrons are placed in low energy orbitals first. And we build up the electron cloud from there. So yes, that means that n equals 1 is lower in energy than n equals 2, and etc., right? But also, the energy of the s orbital is lower than the energy of the p orbital, and it's lower than the energy of the d orbital. The highest energy shape we have is the f orbital. So even with L values, L equals 0, 1, 2, and 3, we still see that idea of changing in energy. Why? Well, it has to do with a little bit of Coulomb's law. How many electrons are we putting in there For the s orbital, we have one option for Ml, so 2 electrons total. When we have the p orbitals, we have 3 options for Ml, which would be 6 electrons total. More electrons, more repulsion, higher energy. For the d, we have 5 options for Ml, so that is 10 electrons total. And for F, we have 7 mLs, so 14 electrons can technically fit in that F orbital group. So increasing those electrons technically increases the repulsive forces between them. It also has to do with a little bit of stuff called shielding and effective nuclear charge. We'll discuss shielding more in depth when we start talking about the periodic trends. I wanted to present it here simply because when we think about a nucleus, there's my nucleus, it has the positively charged center. Let's just put a little plus sign right there. And the electrons orbit around it. Now the n equals 1 electrons, let's just put the 2 there for the 1s orbital, versus the n equals 2. Let's just put another one right here. This outer one is trying to feel attraction to the nucleus. But what it has to compete with is repulsion between the inner electrons. That's what we call shielding. The innermost electrons effectively shield our nucleus. They're like an extra layer around the nucleus. And so the outermost electrons are a little higher in energy because they have to balance this attraction and repulsion. We'll again talk more about Z effective, the effective nuclear charge, and once we start talking about periodic trends. With shielding, there comes what we call penetration. Now again, there's that shielded outermost electron, and here's the inner electron that is effectively shielding. Now, what could happen is that outer electron could come inside and experience more attraction. And it depends on what type of orbital that can do this. We won't get into too much about penetration. Your book does talk about it, but it's a little bit too far in depth for our discussion in Chem 140. So just making sure that you understand shielding is more important for this discussion. Now, here's a general ordering of orbitals for multi-electron atoms. What we see is that the 1s is the lowest energy. Energy is increasing here on the y-axis. So we do start with the 1s. Then we see the 2s followed by the 2p. P's are a little bit higher in energy than s's. Then we see the 3s and the 3p. But here comes the idea of penetration. There is something called sublevel splitting. And with sublevel splitting, what we get is an uneven order of orbitals. The 4 is technically higher than 3, but the s orbital is technically lower than the d's. So what we'll see is that the 3 d's are higher in energy than the 4 s's. Then come the 4 p's, and again, more sublevel splitting, the 5s, and then the 4 d's. No, you do not have to memorize this order. What's really important, again, is being able to use the periodic table. But what I want to do before doing the periodic table is actually use this chart so we can start getting familiar with it to fill in some electron configurations. This is our map. This is the map that we are going to use to say, if I have an element like lithium, lithium has 3 electrons, where am I gonna put those electrons? Well, I always want to start at the bottom, the lowest energy possible. There's 1 electron there in the 1s. I know because of the Pauli exclusion principle, I can put a second electron in there as long as the spin is opposite. I can't put 3 in one orbital, only 2 in an orbital, so then I have to move up to the next one. The off-bow principle says I build up. Well, there are my 3 electrons. I could say that 1 was in n equals 1, L equals 0, ML equals 0, MS is plus 1/2. This guy could be that one. The next one is n equals 1, L equals 0, ML equals 0, and MS equals minus 1/2. That could be my other electron. Pauli exclusion principle satisfied. Those 2 electrons do not have the same 4 quantum numbers. For my last electron, n equals 2, L equals 0, ML equals 0, and MS can either equal plus 1/2 or minus 1/2. It doesn't matter. Choose one just so that you have it written down. And there's that guy. Yeah? That is how we would draw the orbital diagram and the quantum numbers for it. Now, electron configurations are our shorthand notation. We want to abbreviate. In the 1s orbital, there are 2 electrons. In the 2s orbital, there's 1 electron. That is the overall electron configuration. Notice that the overall exponents should add up to the electron count, and that is our final end of the day electron configuration. It tells us a huge amount of information about not only quantum numbers, orientations, spins, and energies of the electrons within this element. Let's try another one. I'm going to go ahead and erase these. I'll keep our data for lithium way up here so that we can move forward. Let's go ahead and look at carbon. Carbon is on the periodic table in row 2. It has 6 electrons. Let's go ahead and build up. 1, 2, 3, 4. There's the off-bow principle and the Pauli exclusion principle working for us. Now we get to degenerate orbitals. Don't forget Hund's rule. 5, 6. So off-bow tells us down here. And to move up. The Pauli exclusion principle says don't put more than 2 electrons on each line. And Hund's rule says, hey, don't pair those 2 electrons, put them in each orbital, 1 in each, because that's what we have room for. Again, X, Y, and Z there. Now, shorthand electron configuration here. 1s2, 2s2, 2p2. We do not see Hund's rule with the idea of the X and the Y and the Z, but we know it's there. It's understood for chemists. This is the full electron configuration then for carbon. Let's do another one. Let's get a little bit bigger. Let's go to sodium. Sodium on the periodic table has 11 electrons. Start at the bottom, work our way up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Notice how I completed the 2p orbitals after I put 1 in each. Then I was able to pair before moving on to the 3s, the higher energy orbital. Full electron configuration, 1s2, 2s2, 2p6, and 3s1. Here's where we get into a really cool observation between, take the whole thing, between lithium and sodium. Notice these two electron configurations. Now, they are in the same group. They are family members. And what do we notice about their electron configurations? Their outermost orbital is an s orbital with 1 electron. There's going to be some interesting facts about reactivity. Let's just move these aside so we can do a couple more. Let's go ahead and do phosphorus. Phosphorus has 15 electrons. And so let's build up from the bottom, and then we'll get into some abnormalities. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 1s2, 2s2, 2p6, 3s2, 3p3. Again, always double check to make sure that your exponents add up to the overall electron count. And make sure you're following the Aufbau principle, the Pauli exclusion principle, and Hund's rule. Now, transition metals. Most of the transition metals follow this lovely category. What we'll see is that transition metals end in the 3D block. They hang out here. Most everybody follows the same exact idea. I want to present some of the irregular ones before we move on. Let's go ahead and look at copper. Copper has 29 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Hop over here. This is the next one. 21. 21, 22, 23, 24, 25, 26, 27, 28, 29. Now, just like Hund's rule from before, d orbitals are degenerate, and so therefore 1 in each before we pair. So copper, we would predict, would have a 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d10. Now here's the issue with sublevel splitting. It's the idea that yes, the 4s is lower in energy than the 3d. But this is not the actual electron configuration for copper. What happens in reality is this electron, I'll highlight that in a brighter color, one of the 4s electrons, one of the previous orbital electrons, can jump up into the 3D so that it can satisfy the complete 3D orbital. I should have said 3D9. Excuse me. So what happens is the 4s2 becomes a 4s1 and the 3d9 becomes a 3d10. So the actual electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d10. This only happens when a d orbital is d4 and it will go to d5, while the previous s goes from s2 to s1. Or the d orbital is a d9 and it will go to a d10, and the previous s will go from an s2 to an s1. It's when the d orbitals are almost half filled and they want to become half filled. There's a stability in half filling the d orbitals. And when the d orbitals are almost all full and it only takes one to become full. Only one electron can move. So copper and his family will see this experiment or this happen. Also, chromium. Chromium has 24 electrons. If we were to predict, we'd see the 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. And what we know happens when you see that 3d4, it's almost half filled. So scoop one electron from the previous s orbital, which would be the 4s, and pop it in that d. With the 5 and the 1. Reasoning for that is primarily because of the reactivity between and the energy difference between the 4s and the 3d. We can see it a little bit better here. They're very close in energy, these two orbitals. And so completing the n equals 3 is highly favorable versus completing just the 4s orbital. Excellent. Now, I said don't memorize the periodic table and don't memorize the order that we saw in this orbital diagram, the 1s, 2s, 2p, 3s, blah, blah, blah. You actually can read it on the periodic table. Here are the n values, 1, 2, 3, 4, 5. Here is the s block, the d block, and the p block. These guys down here, the F block. So let's say, for instance, we wanted to look back at phosphorus. You start, I'm going to highlight so that we don't block, but I'm going to highlight what would be helpful to look at. 1s, 2, 2s2, 2p6. Notice there's 1, 2, 3, 4, 5, 6 elements in that pink block and 6 electrons in the p orbitals. 3s2, 3p3. The third one over in the p block is that final electron for phosphorus. So we can look at any position on the periodic table and really be able to identify where that last electron went. So for instance, bromine. Without even looking, I see he's in the p block. He's in row number 4. So I could predict that bromine has a final electron in the 4p orbital. He's 1, 2, 3, 4, the 5th element over. He should have his last orbital be a 4p5, and everything else is filled before it. That's the beauty of the periodic table. How it was set up did not have quantum mechanics in mind, but it fits perfectly. This quantum mechanical idea is amazing. So looking and reading from left to right, you can actually use the position of the element on the periodic table and understand what its final electrons look like. Now, a couple of definitions before we get into this category real quick. What I want to explain is that full electron configuration that we just did had some completeness to it. Specifically, if we look at things like argon. Argon on the periodic table has an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6. Its outer, all of its electrons are complete in this set. Why the noble gases are so inert, why they don't react, is because there's a completeness in their orbitals. They all end on a p6 filled orbital. And so what we actually can do for any other element, instead of writing the entire full electron configuration, we can write an inner or noble gas shorthand electron configuration. So something like selenium, we could write out the full 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, look at that, inner transition, or the transition metals there, 3p4. But that takes a really, really long time, and it takes a long amount of space. What we could do, instead of writing the full electron configuration, write what we call the shorthand. You take the previous noble gas, and then you write whatever is left over. Notice this is the exact same right here. Whatever's left over, we can write after that noble gas shorthand. Understanding that completeness is important. Now, the inner electron configuration not only helps us to write less, but it also gives us the idea of core electrons, stable electrons. The noble gases are so stable because of that completeness. And what that means is every other element's inner or core electrons are also just as stable. Anything we write after that shorthand, those can be reactive electrons. And so we'll dive into that as we get into periodic properties. Again, here's just the slide on understanding the transition metals. They're in row 4 to start off with scandium all the way to zinc. But again, the d orbitals are always going to be one less than the actual row number. So these are the 3 Ds, and these ones are the 4 Ds. So they're one less. That's one way of being able to avoid the memorization of those periodic elements, the transition metals. Notice again, just highlighted here, chromium and copper's group with its weird, not predictable electron configuration. That's something you do need to know. What I want to talk about a little bit more are the definition of core electrons. These are the innermost electrons. They are going to be stable, represented by a noble gas configuration. And we also have the valence electrons. These are the outermost electrons. These electrons are reactive. So we'll be able to look at those outermost electrons to understand physical and chemical properties. And they include the electrons in the s and p orbitals of the highest unfilled n value. So just to bring up another example, we can look at something like chlorine, which has a noble gas shorthand of neon 3s2 3p5. Overall, 7 electrons in chlorine's valence, 10 electrons in chlorine's core. Whatever is represented by that noble gas configuration, the Ne, neon, is atomic number 10, so 10 electrons for that neutral element. Those 10 electrons that chlorine also has with the same electron configuration are core, stable, non-reactive, innermost electrons. The outer electrons are what chlorine can actually play with and do reactions with. To compare, let's go ahead and just pull a normal transition element, manganese. Its previous noble gas is argon, 4s2 3d5. Notice this is the predicted. It's not, we do not change any of the s's and the d's. Because the d is half filled already, we're stable, we're good. Valence electrons, he's got 2. Notice we don't count the d's. Argon is 18, so manganese has 18 core electrons. These are d orbitals. They don't count. They're not part of the noble gas core, so they're not core. And they're not part of the valence because valence is only s and p's. That's it.
Today, we're going to dive more into the electron configuration, some elemental properties. We'll talk about ion configuration today, and then we'll also be able to discuss our periodic trends. So again, periodic tables handy and ready so that we can dive into the structure of the periodic table and see how quantum mechanics truly emphasizes the benefits of the periodic table and some information we can obtain from it. So electron configurations, like we talked about last time, are pretty much the roadmap to being able to fill up the electron cloud. How does the electron cloud structure look? We can identify our quantum numbers, N, L, ML, and then MS. We can talk about looking at the core electrons, the ones that are complete and unreactive. We can talk about valence electrons, the outermost electrons, and see how those react and why they react. And so looking at some of the groups, we've pulled up a few groups, specifically 6A, or excuse me, 8A, 2A, and 7A. These would be 18, 2, and 17 on the new version of the periodic table, depending on the numbering system that you're looking at. And so elements in that same column, which we called families, have similar properties. We knew that from before, looking at our introduction to the periodic table. And these elements in a period show the pattern that repeats. So again, a period is going to be the row. What that means is as we look going across the periodic table, we can start to see repetition going from left to right, and we can see a lot of similar properties along a column or a family. Now, the quantum mechanical model explains this because the number of valence electrons and the types of orbitals they occupy are periodic. That means that they are repetitive, they are similar. What we notice, especially in the noble gases right here in group 18, the outermost electrons are filled, they're complete. There's a stability in that. And even when we look at neon, its principal quantum number, n equals 2, is complete. Same thing with the n equals 3, the n equals 4, the n equals 5, and the n equals 6. They all have a complete outermost shell. Every electron is paired. Every degenerate orbital is filled. No electrons are by themselves. Now, this is one of the reasons why noble gases are inert, unreactive. We'll talk about more in gas laws with the noble gases. Just noticing their electron configuration already starts to explain their behavior. Alkaline metals, group 2 right here, notice as we go down this group, 2s2, 3s2, 4s2, they all end with an s2. They're filled for their s orbital. Now notice that these aren't meaning that they're completely stable. They're not like the noble gases, simply because when we look at the difference, the noble gases have an s and a p orbital that's filled. Their valence is completely filled. For the group 2 alkaline earth metals, their s orbital is filled, but again, their p orbital is still empty. So there's still some reactivity here. And when we look at the halogens, they all end with one extra space, a p5. And we know that there can be 6 electrons total in that p orbital. And so we'll start to see how these look towards reactivity. Namely, for the alkaline metals, they tend to form +2 cations. They tend to lose 2 electrons. Why? Well, there's 2 valence electrons in their outermost shell. The halogens, group 17 or 7a, tend to form -1 anions, meaning that they tend to gain 1 electron. Why? Because they have 1 extra space in their valence. And so we'll be able to discuss why elements tend to form cations or anions based off of this electron cloud, based off of electron configurations. Electron configurations specifically for metallic elements. Now, if we think about the metals, they do make up a majority of the elements on the periodic table. Alkaline metals are group 1. These are things like lithium, sodium, potassium, etc. Remember, hydrogen is not part of the alkaline metals. Hydrogen is in a special category all on its own. They have 1 more electron than the previous noble gas. So they have an electron configuration of ns1, whatever their n value is, based off of the row number. So lithium is in row 2, sodium is in row 3, potassium is in row 4. They do have an outermost electron in the s orbital, that L equals 0. And they only have 1 electron in that orbital. Now that 1 electron means that it's by itself. It's highly reactive because it's very easy for that noble gas to lose that 1 electron. And then what happens when it loses that electron is the resulting electron configuration is the same as the noble gas. So let's just take lithium for example. Lithium has an electron configuration shorthand of helium 2s1. Now, when we think about lithium forming a +1 cation, that means it lost 1 electron. Well, which electron did it lose? That one. That outermost valence are the ones that can react. We can either add more electrons and become negatively charged, or we can lose electrons and become positively charged. Now notice what happens to the electron configuration of lithium plus 1. It's helium 2s0. But we don't need that orbital anymore. We could just say the electron configuration is the same as helium. There's stability there. We know that that electron configuration is stable. So metals tend to lose electrons so they reach a noble gas electron configuration, a stable electron configuration. The alkaline metals, which we saw previous, they have two electrons more than the previous noble gas. These were things like beryllium and magnesium, etc., going all down that list. They tend to form +2 cations. Now, when we think of beryllium, he's got an electron configuration of helium 2s2. When beryllium forms that +2 charge, what 2 electrons are going to be lost? Those outermost 2. And why these group 2 metals tend to gain a +2 charge is because they have 2 valence electrons. They want to get rid of those valence electrons. And so metals tend to lose electrons based off of how many is in their valence. They want to reach that noble gas electron configuration. Transition metals and intertransition metals are located in what we call the D block. They have valence electrons that are S's, and they also have D electrons. Now, D electrons are not technically counted as valence, but they can react. Their idea of reactivity is very, very unpredictable. And so when we think about those transition metals and those intertransition metals, we want to be very careful with looking at predictability there. We can start to understand their electron configurations, but again, very, very difficult. What they can do is they can lose electrons from the S and the Ds. So something like, let's just pick iron. Iron has an electron configuration of argon, and then dropping down to the 4s2, 3d, and it's the 1, 2, 3, 4, 5, 6 element over on the periodic table. The first thing that iron would do, or what we can imagine based off of what we see, is that iron forms a +2 charge readily. Well, the 2 electrons that he will be losing in order to form that +2 charge are the S's. Always remove the S's first. So iron +2 has an electron configuration of argon 3d6. Now, another charge that iron can form is Fe+3. This is one of the issues with the transition metals. They can form numerous different charges. That's what I mean by unpredictable. Now, iron +3 would lose the 2 from the 4s2 orbital and also 1 more from the Ds. That's where we can say that the Ds can react, but they don't have to react. So we don't want to count them as valence electrons, but we can see that they react in order to form stable cations for those metal transition elements. Now, one reason why we could imagine the +3 charge is favorable, remember what we said about a half-filled d orbital. That's stable. So there is a driving force for stability for those transition elements. It's just not perfect noble gas configuration. Stability could be removing the outermost electrons, the 4 S's, or whatever the S orbital would be for those transition metals. It could also be looking at getting the d orbitals that are left over to be somewhat stable. Half filled or all filled is the most, and we can see other things from there. Unpairing electrons is always more stable based off of our idea of Coulomb's law. Now the p block metals, there are not too many p block metals. The most common ones being tin or lead. These are metals. They're not, we haven't quite crossed the threshold of the metalloids yet, but they have S's, P's, and D's in their electron configuration. Let's just take tin. Tin has an electron configuration of krypton, 5s, 2, 4d, 10, 5, p, 2. Now, when we look at these p block metals, they are located on the far left hand, or the right hand side of the periodic table, but again, the left hand side of the metalloids. And in a chemical reaction, they will lose the s's and p orbitals only to form cations. Now, which one do they lose first? The p orbitals, because we know the energy of the s orbital is less than the energy of the p orbital. So lose the p's first, then we would lose the s's. So we could predict that tin most likely could form a tin plus 2 cation, getting rid of both of those p electrons. And then we could also think about tin forming a tin plus 4 cation, being just left, D's, with the 4d10 electrons. So again, trying to predict is difficult. I don't expect you to do much of it, but I do expect you to be able to look at the order at which cations lose electrons. Essentially, we could say that we lose the last electrons we put in, but again, the transition elements and the inner transition elements don't do that. They lose S's before D's. So that's the one caveat to that. Now, metallic behavior and these electron configurations, what we can start to see with this type of periodic table where it has all of the electron configurations there, we can start to look at their predictability. One thing that we can say overall is that group 1 here forms +1 cations, group 2 forms +2. The transition and inner transition metals are various, but they are cations. They will always lose electrons. And then what we see with our nonmetals is what we're going to call anions. They gain electrons and have negatively charged things. Why? As we move from left to right on the periodic table, we're getting more and more valence electrons. And so we are getting more and more closer to the next noble gas configuration. So instead of chlorine losing 7 electrons, it would rather just gain 1 to gain the electron configuration of its next noble gas, argon. Behavior of the metalloids. Let's talk about those just a little bit before we get more in depth with the nonmetals. Metalloids are located in the P block. They are the steps or the zigzag diagonal line on the periodic table. They can exhibit metallic or non-metallic behaviors. They can either lose electrons from the P and then the S orbitals to form cations, or they can gain electrons. They can do both. So we won't be asking you to predict any of these cation behaviors. Just know that they can do both. They can act like metals or they can act like nonmetals.
For the nonmetals located in the P block, the upper right-hand side of the periodic table, in chemical reactions, nonmetals will gain electrons. And by gaining a negative charge, that's how they form anions. Their resulting ions also have a noble gas configuration. It's just the next noble gas configuration. So let's look at a different one. I know we mentioned chlorine. Let's just go with oxygen first. Oxygen has an electron configuration of helium 2s2 2p4. It will gain 2 electrons to become oxygen with a -2 charge, and that becomes neon's electron configuration. If you wanted to write it out, it's helium 2s2 2p6, and that is just the next noble gas, neon. So there is a stability there again. We can think about iodine. Iodine has an electron configuration of krypton 5s2 4d10 5p5. It will become iodine -1 so that it can become the same electron configuration as xenon, the 5p6. So again, stability in all of those aspects, reaching a noble gas configuration. Halogens, just pulling this group out specifically, they are nonmetals. They have one fewer electron than the next noble gas. So what we usually see is they form the -1 charge. That's a periodic trend that we can understand based off of electron configuration. And how amazing is it that this group or family was already developed 150 years ago when quantum mechanics was only established about 100 years ago. Again, with ion formation, we saw today that we can predict main group elements mostly. Main groups are highly predictable. We can make sense of the transition metals and the inner transition metals based off of what we see. We should know the order at which we remove electrons. But again, we should be able to know the charges of the main group elements. Metals form cations, they're positively charged atoms. The nonmetals form anions, they're negatively charged. We see some of our generic thought processes for all of these. Here again is a periodic table chart of the ions that you should know. By knowing these and the generic trends, what we see is +1, +2, +3, and then -3, -2, -1 as we get over towards those noble gases. These are good to know to help us once we get into our ionic bonds and our covalent bonds, knowing how many valence electrons an atom has, knowing the typical charge it forms is very helpful in order to really understand how those atoms form ions and how those ions form compounds. All right, so periodic trends. We talked a little bit and briefly introduced the idea of the Z effective, the effective nuclear charge, written like this, ZEFF in the little subscript. Now, this is the overall net positive charge that is attracting a particular electron. This is one of the reasons why we know there are different energy levels amongst the principal quantum numbers. S's are lower than P's, P's are lower in energy than D's, and D's are lower in energy than F's. It's because of this effective nuclear charge and the overall idea of shielding electrons. We're going to have different energy levels. Now, core electrons effectively shield
the outermost electrons. And so core electrons are not what we're going to be looking at for effective nuclear charge. The particular electron that we want to focus on are those valence electrons, because those are the ones that go into reactivity. Can we calculate the effective field of the nucleus on those electrons and understand why some are more reactive than others? So the outermost electrons in the valence shell do not shield one another. They will only be shielded by the core. And what that means by being shielded is the idea that when we look at the reactivity, the valence electrons are being on the outside, they do not feel as many protons in the nucleus. Again, nuclear charge, there's protons in the nucleus. And those protons are attracted to electrons. Opposites attract. So when we get into that idea of protons being attracted to electrons, the valence electrons don't feel as much attraction to the protons because of the shielding that is seen from the core electrons. Now, overall, what a periodic trend will be a statement that states what happens. It doesn't explain why. We're going to explain why with our quantum mechanics and the theory behind it. But here's the periodic trend, our first one. The effective nuclear charge increases as you go across a periodic table and stays the same as you descend down a column. So from left to right on the periodic table, Z effective increases. We'll be able to see why. But as we go down a group or a family, the Z effective stays the same. So now we see in this nucleus, we're dealing with a +3 nucleus, so that means we're dealing with lithium. You can do this with any sort of atom that you want. Now, lithium has an electron configuration, we'll do the full one, 1s2, 2s1. What we want to do is figure out, what is this guy feeling? Is he attracted to the nucleus? Is he not really attracted to the nucleus? What's happening to him? How much of the nucleus is he actually attracted to? And the answer here is the Z effective. What we need in order to calculate the Z effective is the actual number of shielding electrons and the nuclear charge. So how many protons minus the number of core electrons. That's what we need. Z, right here, is the nuclear charge. That's the count of protons. S is the number of electrons specifically in the core, and that's how we get our Z effective calculation. So for lithium, the lithium Z effective is 3 + 3 minus 2. Which means the outermost electrons are feeling about 1 proton. It's not a perfect calculation, but it's effective. Now, let's take another atom in that same family. Let's go to potassium. Potassium has an electron configuration. We'll do the noble gas configuration. Argon, 4s1. Now, argon is 18 electrons. Plus that extra 1, potassium has 19 electrons total. So the Z effective here, if potassium is atomic number 19, it has 19 protons in the nucleus and 18 core plus 1 on the Z effective. Same exact Z effective. Even though it's a larger atom, the outermost electrons feel about the same number of protons, no matter if we're dealing with lithium or potassium. That tells us that the reactivity of those outer electrons for lithium and potassium is effectively the same. They're feeling the same number of protons, they're still slightly attracted, but not really, really attracted. Let's do a couple more examples before we move on. I want to move across the periodic table now. Let's go ahead and go to carbon. Carbon is atomic number 6 on the periodic table, and in a neutral element, it has 6 electrons. Helium, 2s2, 2p2. 2 electrons in the core. So the Z effective for carbon is going to be 6 protons minus 2 core electrons, or plus 4 Z effective. Notice that on the periodic table we have lithium, beryllium, boron, carbon. So as we move across the periodic table from left to right, Z effective increases. The reason for that, notice the number of core electrons that we had for carbon and compare it to the number of core electrons we had for lithium. As we move from left to right on the periodic table, the core electrons don't change. But what does change? The proton count. The proton count increases, and therefore the Z effective is increasing. So it's very important to note, as we move from left to right, we're increasing the number of valence. That does nothing to our shielding. We are increasing the number of protons, and therefore we are increasing the overall Z effective. Very, very powerful. We'll do the last one, fluorine, in that row. Fluorine has 9 electrons. So electron configuration is helium, 2s2, 2p5. For the Z effective, we have 9 protons now in the nucleus, but still only 2 core. So looking at moving across the periodic table, we can see the increase in the Z effective. Second trend is atomic radii and how does it actually affect our size of the atom. This is the wrong chart. There it is. Radii of atoms. Let's first look at the gray circles here. The radii of atoms, as we move across left to right on the periodic table, across a row, we picked out here group 1, 2, and 3 just to show the similarities amongst these, but it would extend all the way across to group 7A or 17, the halogens. And what do we notice? 152, 112, 85. These are in picometers. So the size of the atom decreases as we go from left to right. Well, what is causing that? The Z effective. As the Z effective increases, that literally means the electrons on the outermost shell are feeling more of the protons in the nucleus and therefore being held tighter. So as we think about the Z effective, yes, we're increasing the number of proton count. Yes, we're increasing the number of electron count, but the actual attraction between those protons and those electrons, the Z effective, is increasing as we go across the row. And so therefore, the size of the atom decreases from left to right. As we go down a group or down a family, what is important to note is that size is increasing. Well, Z effective does not change going down a group, but what does change is the principal quantum number N is increasing. We are actually physically putting these valence electrons in a totally different shell. And so as n, the principal quantum number, increases, we see the size of the atom increases. We will see this repeated over the course of the next few periodic trends. As we go across the row, Z effective increases, so electrons are held tighter. As we go down a group, the n value, the principal quantum number, is increasing, so electrons are further away from the nucleus. Now, notice the red dots now in comparison to the gray. If we look at the relationship here, lithium to lithium plus 1 cation, or beryllium to beryllium plus 2 cation, cations are always smaller than their parent atom. And the reason for that is because when a cation forms, they are losing electrons. So we are looking at losing the valence electrons. So there are less electrons to hold in the atom, and so therefore the size decreases. We're removing those electrons from the outermost n, and so we are decreasing the actual distance away from the new outermost electrons. So cations will always be smaller than their parent atom or element. Here again, we see the other half of the periodic table, group 6A and 7A, or 16 and 17. As we again move from left to right on the periodic table, we see that size decreases because the Z effective is increasing. Electrons are being held tighter, and therefore more attraction. Being held tighter, therefore they are closer to the nucleus. Not very much, a couple of picometers, but still important. Get all of them down in there. Now again, looking at the relationship between an anion and its parent, anions will always be larger than their parent. And that's because, again, we're putting more electrons in the outermost shell, taking up more space, having to share that Z effective a little bit more. Their parent being the neutral element. Excellent. Periodic trend number 3, ionization energy. This is a potential energy. This is looking at the minimum energy needed to remove an electron from an atom or ion in the gas phase. Notice how it's specific to removing an atom. So I'll rewrite this reaction. Some sort of atom in the gas phase going to become a cation, specifically a cation. This is what we call ionization energy. If it's the first electron removed, we call it ionization energy 1. Now, we can remove more electrons. We can say that M plus 1 cation in the gas phase can go to become an M plus 2 cation in the gas phase. Notice how both of these are losing electrons. Which one or what number we're on, that ionization energy is always going to be positive. Energy is required to remove an electron. Why is it required? Because when we think about removing an electron, that electron is attracted to the nucleus. It's like a magnet on the fridge. In order for that magnet to be pulled away from the refrigerator, we have to put energy in, which is endothermic. It requires energy. Now, notice here on the same first and second ionization energies, they actually put the electron there as a product, as if it's being pulled away from the metal itself. Excellent. Now, everything has an ionization energy, but what I like to look at in this chart, as we move from left to right on the periodic table, from lithium all the way up to neon, or sodium all the way up to argon, these are moving left to right across the periodic table. What we notice is that ionization energies increase. Across that periodic table. Why? Why would it be harder to remove an electron? Why would it cost more money to remove an electron? And that is because the Z effective is increasing. Those electrons, as we move across from left to right across the period, the Z effective is increasing, which means those electrons are getting held tighter and tighter and tighter. The atom is getting smaller and smaller and smaller. Those outermost electrons do not want to leave. It costs a ridiculous amount of money or energy to remove a fluorine electron to become fluorine plus 1. This is why we would never see nonmetals form cations. They just don't. Nonmetals don't like to form cations. Now, as we go down a group, ionization energy decreases down a family. Or a group. Why? Because N is increasing. Way back, we talked about playing Red Rover. And remember, if we think about playing Red Rover, we want to be held as tight as possible when we play that so that our neighbors can't crash through and break apart our arms. Now, as the atom gets bigger and bigger and bigger and bigger, yeah, the Z effective is staying constant, but the actual energy of those electrons in the outermost orbital is increasing because of N. So yes, it's feeling the same attraction to the nucleus as we go down a group, but the actual size of the atom is important to discuss. And so why we see the ionization energy decrease, it doesn't cost as much to remove an electron from potassium as it does from lithium, because potassium is a much bigger atom. Here are some generic, another way that the book shows that. Highest ionization energy here, lowest ionization energy down here. So we see this generic trend of increasing up a group and across from left to right. Again, for the same reasons as before, either the Z effective or the principal quantum number. Now, trends in succession, the second and third and fourth ionization energies. It depends on the number of valence electrons. So pull out here nitrogen versus oxygen. Nitrogen has its valence right here, 5 electrons. Oxygen has 6 electrons. And what we're really wanting to specifically look at is how many in the P's. 3 P's, write it the other way, P3 and P4. So what we notice for this is we're going to have a very specific difference between nitrogen's 5th ionization energy and 6th ionization energy, because we can remove 5, but we definitely don't want to go into the core. For oxygen, we'll see a big difference between the 6th ionization energy and the 7th ionization energy. because again, we can remove the valence, but we don't want to get into the core. We can see that with sodium and magnesium. Sodium has 1 valence electron. So it's a very small number for its first ionization energy, but start to think about removing a second one. These are core electrons. We never want to remove those. Magnesium has 2 valence electrons. So we see a first ionization energy that's small and the second one that's a little bit bigger, but look at this huge jump now between the second and the third. We don't want to go into the third for magnesium because we only had 2 valence. We're gonna start to dip into the core. So there will be always a large increase when the core electrons are starting to be removed. So valence electrons have relatively low ionization energies. The biggest jump happens when you have removed all the valence and you're trying to remove a core electron. We can see this step ladder as we move across the periodic table. This is the 3rd row, starting with sodium and then magnesium, moving all the way across. Looking at this step ladder, we can see that once you've removed all of the valence, sodium has 1 valence, magnesium has 2 valence, aluminum 3. What we notice is that there's the biggest jump on 1 more than its valence. So sodium has 1 valence, its biggest jump comes at the second ionization energy. Chlorine has 7 valence. The biggest jump is going to come over here at ionization 8. Big, huge. Don't even try. Excellent. Electron affinity is less predictable, but I like to talk about it because it's the opposite of ionization energy. It's the energy associated with an addition of an electron. So notice that atom gaining an electron so that it becomes a -1 anion. And the energy associated with that, we call it electron affinity, and they will always, or most of the time, be negative, releasing energy. Some may be endothermic, and this is why this topic is not as easily accessible for us in this class. We won't use electron affinity that much, and we'll see some numbers and show how they're really not helpful at all. The more energy that is released, what we do call that is a larger electron affinity. That's another reason why it's not as fun. The more negative the number is associated with that energy, it's negative because it's being released. We call that a larger electron affinity, means that that atom loves electrons a lot. So here's the chart. In general, electron affinity increases as you go from left to right on the periodic table. What that should tell us is that metals do not like electrons. Nonmetals love electrons, which makes sense. Nonmetals tend to form those negatively charged ions, right? We love electrons. Here's my heart. And nonmetals tend to form +1s, or metals tend to form +1, +2. We don't really care for electrons. We'll say it nicely. We won't use the word hate here. I don't like to spread that out into the universe. Halogens have the highest electron affinity for any period. They love electrons. They want 1 more electron. They're going to try their hardest to get that 1 electron to reach noble gas phase. They're so close. So electron affinity becomes more negative as we move from left to right, meaning that more energy is released as we move from left to right. We don't really want to talk about going down a group. What we tend to see is, it starts to look like it decreases, like there's a more positive value. But let's just, look at these abnormalities. Yeah, they're very weird. So we don't talk about going down a group or a family at all. Has a little bit to do with size. It has a little bit to do with the valence. but we won't talk about them. Now, the last periodic trend we have is metallic character. Metallic character tends to increase as we go down a group. Why? It's because, again, the atoms are getting bigger. It's because ionization energy is decreasing. So there's a lot of reasons for that metallic character. The most important two trends I want us to know are the first two, atomic radii, and first ionization energy. Metallic character kind of makes sense with the idea of ionization energy. Metallics meaning making cations. So if it's easy to make a cation, then it means it's a very good metal. That's pretty much it. Electron affinity, there's no definite trend moving down a column. That's why you see a blank there. But moving across a row, you see that there is that general trend of decreasing, more negative. Lovely. So this chart of summary of the periodic properties you should know, but the first two you should know intimately. You should know the reasons why in terms of Z effective or the size of the orbital. And that's all I have for you today. Thank you so much for joining me.